Thanks everybody for coming to this lecture. This talk was inspired by, I had been doing fracture mechanics in rock. It was part of my PhD, but it was mostly experimental work. And then it probably wasn't until I moved, after a couple of summers in Arizona, I decided to buy a house in Colorado. So up at 9,000 feet. So really, when I was starting to hike around and all that, I would see these unstable structures. And every once in a while, I'd climb up the hill to where this kind of thing was, and I often looked behind it, and there was nothing there. It basically was just being held up by. So I got very interested in rock bridges. That was kind of the thing I did, and so applying this fracture mechanics to rock bridges works very well actually. And of course, this is another example. This is a very famous example in Yosemite. This is a couple of these famous flakes. This is exfoliation fracturing on the cliffs of Yosemite, and the climbers love these. And I didn't really realize that. I gave a talk and I mentioned the blue flake, and then one of the professors was like, "Oh yeah, I've climbed on that all the time." And I go, "Wow, that's pretty interesting." Anyways, these are similar in the sense that. The question really is, how stable are these structures that at the bottom, there's a hotel down there, there's campers, there's, all sorts of things going on, as well as these climbers. So, Greg Scott and his colleagues have been investigating this, and I'll talk a little bit more about that later.
Figure out how to advance.
So sometimes if you first do it on the screen.
Oh, just do it once on the screen. Okay.
Yeah.
And then it decides to get it.
Yeah, exactly.
And then let's see. Yeah, okay. So this, as Jill said, this is a Johns lecture, and we're honoring the legacy of Richard Johns, who was a professor. He was a dean. He'd been at various institutions over his career. He did a lot for the field of applied geology. So he was really a spokesman for applied geology, and it's so important to get the word out, to get people into this field. More so than ever, all you hear about is computer science, but believe me, we are important. Applied geology is very important today. So you can get another degree in computer science, but at least have one of them in one of these. So anyways, the lectureship was established in 1988. And the funds were coming from two foundations, the AEG Foundation and the GSA Foundation. And the idea of the funding was to support lectures to go around and give lectures. And you spend, whatever that period of time is, maybe 5 or 6 months going around and giving lectures. I know there's some record holders in terms, like Scott, in terms of how many talks they might have given. I might give 45 or 50 talks, I think, in what I do. I give about 12 or 15 talks so far. So, so I am the 37th Johns lecturer, and what's great about the Johns lectureship is we're all different. Every year is someone different. Some of them are academic, like I am. Some of them are practitioners, or in between. And so it's really, that's what makes it so sort of special. So the question is that what perspective do I bring? And as Jill said, I'll give a little intro to myself. So what do I bring to the Johns lectures? Really, I've been a rock mechanics guy. So rock mechanics, geomechanics, rock engineering, that's kind of been my field. And I've been sort of doing one thing or another for about 45 years now. It includes, I started out actually consulting in a geomechanics consulting company before I went back and got a PhD. I got a PhD, then I did a postdoc at Lawrence Berkeley Laboratory in Berkeley, wonderful place. And then I started my academic career at the University of Arizona, Department of Mining and Geological Engineering. I've been there 35 years. I retired a few years ago. I still teach one class. The stuff I'm going to talk about today is related to that one class that I teach. And then I had the really nice experience of having a successful entrepreneurship as part of my research. So the research was going along pretty well. We were doing this. One part of it was doing this sort of analysis of fragmentation due to blasting and things like that, and the mining industry was quite interested. And so it turned out me and 3 students started a company. It lasted for 22 years. We sold it to Hexagon Mining Division. And so that worked out pretty well. So it's kind of a nice experience there. And then since retirement, I've all, I kind of, me and my colleague, we sort of had discussions, and we kind of really wanted to sort of learn about AI, how it could be applied to applied geology, things like that. So that's kind of what I've been doing for the last couple of years. And I'll explain more about that as we go. So these are the 5 talks that I have set up. So the idea is I go to a place, they decide which talk I give at that particular place. So today I'm giving this one on unstable. Why is that unstable rock still standing? And it kind of goes together with the everyday geospatial one I gave last night, because I teach a class now, an online class. First half is pretty much the everyday geospatial, and the second half gets into more of this rock fracture mechanics stuff. I teach an AI talk that's based on the stuff I've been doing the last couple of years, where I just kind of throw out some creative stuff and see what people think about it. I also have just sort of a basic talk on rock mechanics. And then I do have one on entrepreneurship, which again is more of this creativity. What do you, do something interesting. And, one thing that students can actually do while they're students or soon afterwards is start a company. That's one of the things I talk about a little bit. So that's that. So the basic theme of all 5 of those talks is really that applied geology more important than ever. In the idea that it's kind of themed around the idea of climate change. And I show this, I don't know if you're familiar with this, is Dave Petley's landslide blog. And he keeps track of unfortunately fatal landslides. And you can see in 2024 was far greater than any of the previous years in his database. So, and this is not just landslides, it's happening to fires and flooding and debris flows and rockfall and everything else as well. So that's kind of the idea. So my talk kind of in some sense addresses that. So fracture in rock are an important aspect of many of these geological hazards. As you can see, here's a nice wedge failure along a highway in Idaho near Stanley, Idaho. And what's interesting is that this slope is littered with rock bolts all over it. So it's a pretty unstable slope, you can tell. Anyway, so that's kind of the idea. And today, what I really want to do, fractures can mean a lot of different things to different people, fractures in rocks. And I focus on what they call engineering scale. So let me just define a little bit what I mean by engineering scale. So the idea is that, it's more about engineering jobs. It's more about slopes. It's about underground excavations or a dam foundation or, kind of that scale of fracture we're talking about. And even within that, I differentiate sort of 2 types of fractures. You've got sort of the geologic fractures, which are joints and bedding and things like that. And then and those have been there for a long time. But now what you do is you make a slope, and suddenly you change the stresses, or you change the amount of water that goes in it. And now you get additional cracking, which is in our time. And so that's what I call new fracturing. And you can kind of see, this is probably some existing fracturing in the rock mass. And then you can see, and there's some kind of overhang, and we're getting some additional cracking and deterioration of these slopes. And again, it doesn't have to be a slope. It could be any of these places where we have rock structures. And so that's really what I'm going to talk about, both those things. I'll first mention just a little bit about pre-existing fractures, and then I'll go on to new fracturing. And what I won't talk too much about is micro cracks and things like that, but they are very important. I give this example. This was a laboratory test where we look at a borehole breakout. Borehole breakout is very important for the petroleum industry. You drill a hole, you get deep enough, it's bound to break out at a certain depth as the stress gets larger. And what's interesting about this one is you do a test, and then you stop the test, you inject some kind of resin to keep everything falling apart, and then you can slice it open, and you can see that in fact you wouldn't necessarily even be able to see that borehole breakout from the traditional methods, which would be some kind of a caliper or some kind of a camera. So a lot going on behind the scene you don't even necessarily see using traditional methods. So kind of important. And then of course we have the more tectonic type of we call fractures, these, which is like normal faults and strike slip faults. And then I think this is the San Andreas faults at some place in Southern California. All right, just real quick, again, this is more review stuff here. What are some of the properties of engineering scale rock fractures that we measure? I think one of the most important things is the size of the joint, the spacing between fractures, or the size of the blocks. Those are kind of similar things. And I just give you 3 examples here. This is sort of a mining environment. This is from a mine in Arizona. You see the alteration, and the block sizes, tend to be smaller. This is a quarry in Colorado, where that rock was being used, maybe in a statue in downtown Denver or something like that. And you see there's a person here for scale, and we see this large fracture spacing. This is a foundation of a dam in Puerto Rico. The Army Corps is involved in the Portuguese dam in Puerto Rico, and this shows a kind of a very grungy looking rock mass here with very small spacing. We know about joint orientation. That's the second thing we know. And, we often see, when I tell students to go out and image, find a place with at least 3 good joint sets. And so you're going to get these nice blocks just to make your life easy. Doesn't mean that it's always that way. And you see nice cubes that represent, the joint sets you might see. And then we get steeply dipping joint sets that shows up on both sides, things like that. And then you have what's in the fracture. So is there alteration? Is there some kind of fill that could make it weaker, that can make it strong? Is there a roughness? And then another thing I'll come back to is aperture. I look at aperture as kind of the spacing, like how open a fracture is. And for me, aperture, I often use as a measure of degradation of slopes. And so you can even see that here where there's some kind of a block, maybe movement or something like that. These are hazards associated with injuries, fractures. I went through these last night, so I don't want to go too much detail, but this is a big wedge fair along the $1 million highway in Colorado. If you haven't driven that, that's a beautiful highway. This is plane failure in Tennessee. Vanessa Bates was the head of the DOT in Tennessee, I think, at that time. This is toppling failure in Northern California. This is rockfall right outside this Hanging Lake Tunnel in Colorado along Interstate 70. So this is what we call a high risk area. Thousands of cars going along this every day. And when you look to see where those rocks came from, they came from about 1,000 feet up. And a lot of them were loose, kind of like the picture of Yosemite, and held up by small rock bridges. This was the Glen Canyon Dam. This is from the Glen Canyon Dam looking downstream. And there's a big piece of rock here. Again, it's one of these maybe about to fail kind of things. It's a big piece of rock. It's shaped like Idaho, so they call it the Idaho rock. And when you go along the bridge and you look behind it, again, there's nothing there. It's kind of like air, and you see this sort of rock bridge holding it up. This is debris flows that we had in 2007 in Tucson. And if you go to the very tops, I had students go up to the very tops and look for triggers, and we saw definitely some rock triggers to these debris flows there. So I use this example of that slide in Tennessee, just to kind of demonstrate. What I want to do here is I want to show how we do a traditional slope stability, and then I want to compare it with what we do later when we add rock bridges. And we're able to add what the additional strength is due to a rock bridge. So I do this very simple thing with playing field. This was a playing field again. They set up a video camera. It looks like it's raining out there. You see a pretty big mass of rock that fell. And this is my explanation for factor of safety. So the idea of factor of safety is you want to design stable slopes. And the question really is, how stable is a stable slope? Is it about to fail? Is it not going to fail in the next 10,000 years? And so we have this concept in engineering of factor of safety. And really, it's basically strength divided by stress, and it's in the place that may be failing. So in our case, we have a slope with some big piece of rock on top, and there's a fracture. And that's where we're trying to evaluate the strength and the stress. And so the strength will be two parts. It'll have a cohesion part and a friction part, and that's represented by this. And then the stress will be the weight resolved into this shear direction, and that gives me this. And so I get a very simple factor of safety equation. When sliding, it's not so simple as soon as you go to something like wedge sliding. Anyways, I put some numbers in here, and we see that you can get a factor of safety of 1.31, which means it's more than one, strength more than the stress, therefore it's stable. We need to add water. We always need to consider the effect of pore pressure, and so the pore pressure will affect the top term, will not affect the bottom term. Anyways, you could put a pore pressure in here that might be realistic for that slope if it was if all the fractures were full of water. And we see that the factor of safety goes to 1.0. So that kind of gives us some information. And is that enough? It's not really enough, because if you look at this picture, this is kind of the aftermath. What you see is it slid on one fracture over here, it looks like it actually slid on a different fracture over here. And then over here, it didn't slip at all. So why within, 100 yards or so do you get this difference? And things, that's the joy of rocks. They're so heterogeneous. Everything, there's a lot of variability in the strength, variability in the pore pressure. Could be raining more in one place than it's raining in the other place, or it could be trees or something like that, more tree roots and something like that too. And then you could be fracture orientation. So we do this thing called probability of failure. And this is just a simple example where I could take some of the variables. I can just assume they're normal distributions with a mean and a standard deviation. I make up a spreadsheet of maybe 1,000 rows, and in each one I randomly pick from these 3 normal distributions, and then in each row I put it in that simple little formula. And if it's above 1, I put a 0 here, and if it's less than 1, I put a 1, and I add up all the ones, divide by the total number, and that's the probability of failure. And so you can see for this one I had, without water, it was about 13% probability of failure, and with water, it went up to 30%. And then you can ask the question, well, what's a good number? What do I want to design with? You give me some number. And the point is, there's not a magic number for everything. It really depends on the situation. If you have a low-risk highway that doesn't have much traffic, that may have 1 factor safety. If you have an interstate where you have a lot of traffic, that may be higher. If you're building a dam foundation, you might even have a higher factor safety. So it really depends on the situation, and that so on. Okay, so now this gets me to really the fracture mechanics. There's another fracture property that's kind of central to today's talk, and that's persistence of the fractures. So of course, as engineers, we often model these fractures as very simple things, but of course, they're not really simple things like that. In most cases, the fractures are not fully persistent, and so you end up with more something like that. And what happens when you have non-persistent fractures is you're going to have 2 things. One is at the tips of these fractures, because there's a load due to the weight and other factors, there's going to be stress concentration, and that's going to drive new fracturing. And then the second thing is they're going to be rock bridges. So what I mean by rock bridges, there may be a big block that's ready to fail if just this one bridge fails. It's the last thing to fail. So, I'm very interested in that idea of what's the last thing to fail. And we often see it because we see a block comes down and there's one little corner that's a lighter shade than everything else. And that probably was the last thing to fail. That's the rock bridge that was holding it up for some period of time, and then it decided to go. So that's a lot of what we talk about here is this sort of last thing to fail. Okay, so here's a little bit on how fractures grow. Just kind of, I'm trying to do a little fracture mechanics with the general audience. We'll see how this goes. So the ideas I'm showing here is tensile crack growth under both tension, under pure shear, and also under compression. And I have a little trick I show you just to make it a little easier to figure out what's going on. So under tension, I think we can understand that we're going to get this crack to grow. When I put it into shear, we get these kind of interesting cracks that grow on both ends. And one way I like to look at it is if I put that shear direction right on the crack, then you can see that it's kind of pulling on one end and pushing on the other. So I kind of put a plus and a minus, and on the bottom, I put a plus and minus. And now you can see where those 2 tension cracks are going to come out. Similarly, you can do it if it's in compression. You kind of have the pluses and the minuses, and where you have the pluses, that's where you get thing. Now, fracture mechanics, anyway, and then the other thing is we see evidence of the same thing. We see these horsetail fractures in the field. And again, that tells us the shear direction. And also we can do tests. Plexiglass is nice because it's nice and clear and you can see the fractures, and we get that very similar idea. Fracture mechanics allows us to really, that's what it can do. It can tell us exactly how the cracks are going to grow and when the cracks are going to grow. And so we have these 2 things. One's called the stress intensity factor, and the other thing's called the fracture toughness. So there, it turns out, why people like fracture mechanics is because the formulas are very simple. And why are they simple? These formulas really tell us about the stress at the tip of the crack. And so that's where the crack growth is happening, at the tip of the crack. And so they're no good anywhere else. And so, but that's okay because that tells us how the crack grows. And because they're only good at the tip of the crack, these are asymptotic formulas. They're very simple. So you can see the stress intensity factor for this tension is just this. The one in shear is almost the same. Here's the one, these are what's called single mode. And then you have this one in tension is actually mixed mode because it has both a K1 and K2. And K1 is when you're forcing it, you're opening it in tension, and K2 is in shear. And then what you do is you just take these Ks, put them in various forms. This is just a couple of the formulas, and they give you the stresses at the tip. So let's, I'm going to show just a little equation. I don't want, I just want to demonstrate how simple it is. So here's a simple way to calculate when these cracks will, or what angle the cracks will grow. I basically says, I look around the tip of the crack, I go from minus 180 to 180, and I just look for where the tension is the highest in that angle. And so you can either do it in the spreadsheet, but you can also, this formula is so simple that I can just take the derivative, set it to 0, and then you can see I get a nice angle of 70.5, and that's kind of what we see many times when we see these fractures in the field. So anyways, very simple. Please ignore this formula just to demonstrate that that's why people like fracture mechanics, because some of these things are quite simple. Now, the other thing is we need to know, so we know the angle the crack goes. The other thing we need to know is what load. We know if the load's not big enough, the crack won't grow. We got to have enough load. So we have this thing called fracture toughness. And so when the K1 bigger than a critical value, which we call the fracture, and this is a material property, and so you can do tests to determine this. And in this, some of the examples I'll show, I just use 1 megapascal square meter which is a typical value for a brittle rock like granite or something like that. I just give you an example. We can predict the tensile strength of granite. I assume we have a granite with maybe average grain size of 1.5 millimeter. And we often see micro cracks that kind of show the same distribution because a lot of cracks are on the grain boundaries. So I'm going to assume that I have thousands of randomly oriented micro cracks with an average length of 1.5. It's very simple formula. I just take my formula, I set it K1 equal to K1C, and I solve for sigma, and that gives me a formula for when that crack will start to grow. And I see that it's about 20 megapascal. And I say, well, that doesn't seem right. It's too high for the strength of granite. And what the reason is because there's bigger cracks. So if I have an average, it means some cracks are bigger, some are smaller. And it turns out the tensile strength of rock depends on the larger end of the spectrum of cracks. And so if I do a little calculation here, if I have 4,000 cracks and I assume a certain standard deviation, what's the likelihood having a crack 3 times the average? And it shows that there should be at least 2 of those. And so all I need is 1, and then the strength will be lower. It'll be 11 megapascal, which is a more reasonable number. So anyway, that's kind of the idea. So now let's do 2. Now we've formed the rock bridge. So now let's take 2 of these discontinuities with a gap in the middle, and that's the rock bridge. And again, these discontinuities don't have to be parallel, but the ones I show is parallel. So when we do that, we form a rock bridge, and there's 3 types of rock bridges we have in this case. We have a tension one, a compression one, and a collinear one. And so the tension one is here. So you can see when I go across from one crack to the next or discontinuity, I step to the left and I have a certain shear. And now I can draw my little diagram again with the pluses and the minuses. And you can see that there's both pluses on the inside. So that's going to be very easy to break in tension. So this is what we call a dilational bridge or a tension bridge. And this one has tension in the bridge, and so it will fail in tension. And you can see evidence of this in the field. Same thing. You can also do modeling and show the same thing. Now, when we go to the other type of bridge, the other type, now I go across and I step to the right, same amount of shear. And now I put these things, and you see I get all minuses in the bridge. So now there's compression in this bridge. It's going to be much harder to fail, but it still will fail. And this shows some field evidence of what happens when you get one of these. Collinear is the same thing. You can see that the tension cracks actually want to grow away from the bridge. So this bridge doesn't really want to fail, but it will fail eventually if there's enough deformation. But it's a more complicated things. And we find that shear failure tends to be more complicated than tensile failure. You often get a rough surface. You also get shear cracks. That's different than, so that you can actually get cracks that grow in the shear direction. Again, this is like a more Coulomb failure. You can see again this kind of roughness to the fracture that we often get. But this is a great case I show here where you actually get a crack that grows in the shear direction. So it's again, you do the same technique. You look around the crack tip and you find the location that has the highest shear now, not the highest tension. And you can figure out where the crack should grow. And here's a test. This is a shear test we can do in the lab. This is a really beautiful material that we use for testing sometimes. This is the Coconino sandstone from the top of the Grand Canyon. You see this cliff forming member at the very top there, and that's the Coconino. And when I do these are just notches. I put it in shear, and when you see this thing, it looks like it's a crack, and you'll notice it's coming from the negative side of that. And so it's a shear crack. It's not a tension crack. You can see here's the tension crack right there. That's the tension crack. And similarly, there may be one here, but that's actually shear crack. So that's pretty neat too, that we can talk about shear crack. So this is what I really wanted to get to. So what strength does a rock bridge impart into, like, if I'm doing slope stability and I've got a big plane fit and now I introduce one of these bridges, how much strength does it increase? And again, it's a very simple calculation we can do. We take the formula. Here's the formula for the stress intensity factor for one that has normal stress and shear stress. All I do is I say K2 equal to K2C. I'm doing a shear one, but you could do this with K1 as well. And you solve for tau, and you see this nice relationship. And this is where the cohesion normally is. And so the cohesion then, due to a rock bridge, is this right here. And so it depends on the toughness. It depends on the size of the bridge and this ratio of A over W. And you can rewrite it in terms of A over W, which is nice because A over W is the percent of rock bridges. And this is where you really get to see some meaning. So I'm going to use 1%. So I'm going to say I have a big plane. It's just a regular plane for plane failure, but I'm going to assume 1% of that area is made up of these rock bridges. And so I can just put some numbers in there, and you can see I can get a cohesion. And now I can put that cohesion in the regular slope stability formula I showed you before. So now what we do is we take the same formula I showed before, but for the cohesion, I'm going to use this formula. And you can see that with no rock bridges, the factor of safety using these parameters would be 0.69. When I add 1% rock bridges, it goes up to 1.8. So it's really quite a difference between, so it adds a lot of strength. And that's one thing we kind of see. We see these unstable structures and we wonder, is that small rock bridge enough? And in many cases, it looks like it is. And that's good news. And that Greg Stock figured that out too. I'll show you that one later. Oh, this is Greg's stuff. So this is Greg Stock. He actually talked to me a little bit about the fracture mechanics, and I think obviously Steve Martell as well, and maybe lots of other people kind of contributed. But he looked at two of these flakes. He looked at the Butte flake and the Texas flake, and they use a lot of things. They instrument these a lot to do different things. But one of the interesting things he did was figure out how to use thermal imaging to figure out the size of the rock bridge. And so it's very tricky because you have to do it at a certain time of day when there's a thermal contrast between the bridge and the rest. And so that early in the morning, they would get a nice thermal contrast, and they kind of figured out where these bridges were, both on the Texas one and the Butte one. And so then you can see they're doing some fracture mechanics right there. This is in this paper, 2019. Anyways, the bottom line is this one is quite stable, the Butte flake. And you can tell that because the percent of rock bridge is quite high, actually. And it's a smaller flake than the Texas flake. Anyways, this is what he got in his paper, but he had a pretty small stress intensity factor and not even close to the K1C. So you can tell the climbers, that one's probably pretty stable. Texas flake, on the other hand, actually, I didn't put the formula here, but it actually showed that it had a factor of safety less than 1. And so I remember I saw some headlines in some of the climber things. Texas flake may be unstable. So I don't really know. He may have done other work since then to try to do. He admits that he doesn't think the model he has for the Texas flake is very good. But anyways, very interesting stuff. So one way to characterize rock bridges would be using this thermal technique. It works very good on these flakes, but if the slab is too thick, it won't work. So this just happens to have the right characteristics that it worked. Here's another technique that I've used before, and that's using point clouds. And so the idea here is, this is along that $1 million highway. This is a quartzite, but we get these big fractures, and there's a lot of roughness. And some of the roughness, when I see roughness that is structurally controlled, that usually indicates it's rock bridges that have been broken. And you can see that here. There's a lot of evidence that a lot of this roughness is coming from rock bridges. So then you should be able to at least historically, figure out what the percent of rock bridges was on a fracture like that. And tensile cracking tends to produce what I call random roughness, whereas this is more of what I call structurally controlled roughness, which probably means that they were intact rock bridges originally, and then they were broken. So that's one method. Another method is just to look at color. We've all seen this on these places where you can kind of see the last thing that fell. This one's an interesting one here. This is quite a big block that fell, and it looks like it was really just this little tiny piece at the very bottom that was holding it up at the end, sort of the final rock bridge that had to go, and so on. And so, there's a lot of evidence. And some people can look, I'm not very good at this, but some people can look and see that in these places, I see indications of shear. And in these places, I see indications of tensile fracture. And that would be an indication, so there may be people that are good at looking at these fractures and telling the difference in shear and tension. And you can also use that. Anyways, so now let's get to the interesting part, which is the time dependence of these slopes, because that's always kind of been a mystery. And we have techniques. I'll give you this example of this is kind of the famous example. This was 2013. This was the Kennecott mine. And basically, this was considered one of the biggest landslides in North America, this failure. It turned out that I was at the bottom of that slope 2 weeks before with a field trip. I had like 20 students with me, 2 other faculty members. We were on the other end of the pit at the bottom. And one of our alumni who was taking us down there, she pointed up to that slope and said, it's going to fail in 2 weeks. And it failed in 2 weeks. And it failed in 2 weeks. So, I wouldn't necessarily tell the same story in a mining meeting, because it sounds like we shouldn't have been down there. But that's the truth. We were down there. And so what it is, basically before the failure, they're using this slope radar very carefully, very accurately measures the movement going on. And you start to see this acceleration towards failure. I mean, this happens in all materials before they fail. They tend to accelerate in terms of the velocity, before failure. But it turns out that if you plot inverse velocity versus time, we often see a straight line that points to the time of failure, which would indicate that if you were here with just a little bit of data, you could extrapolate it all the way. I mean, theoretically, you only need 2 points, velocity points, to do it. But the reality is, with rainfall and other things, it moves around. Now, there's a few people that have developed equations related to this. This is the famous Voigt equation, which is Barry Voigt from Penn State. He shows that when alpha is equal to 2 in this formula, again, he's talking about any kind of material, whether it's geologic material, anything, obeys this kind of rapidly acceleration before failure. And when alpha is equal to 2, then we get this straight line behavior. And there's been many papers on landslides where they figured out what this alpha value was, and it usually is close to 2. So that's one thing we do see in rocks often. And fracture mechanics, as I'm going to show you in a minute, provides a little bit of clarity on this topic. So let's keep going. So the idea, again, is going back to this figure I showed. We have degradation of the slope over time, and it's due to many factors, but it's a mechanical thing. And so it's got to do with forces. And so you have forces from many different things. Obviously, one of the drivers would be gravity, the pore pressure due to rainfall, freeze thaw, seismic, roots of vegetation. We have, thermal stresses. These are all drivers of force that's going to cause these stress concentrations at these different places. And then you also have changing material properties, because there's chemical weathering going on, that will also influence the degradation. So you have all that going on. But the idea is that with time, the factor of safety should decrease and the probability of failure should decrease. So we do this thing in fracture mechanics. It's called subcritical crack growth. And so basically the idea is that even when you're below this critical value, you still get crack growth. And there's a lot of people that have had their career based on really sort of figuring this out, what's going on. This shows a particular lab test that people do in the lab. Actually, this was in our lab we did. And this is crack velocity versus K1 over K1C. But what's interesting is it's a log plot, and it shows a very linear behavior. And that implies a power law. And so, that implies a formula like this. So there's this famous Charles law. It says the crack velocity is some constant, K1 over K1C to the n. And what's interesting about this one is when you do these tests, the n value comes out very high, like 30. And what that means is that nothing is really going to happen. This thing's going to be, just basically zero until K1 starts to get close to K1C, and then everything. And that's kind of what we see in reality too. And so it kind of mimics the way that we kind of are familiar with how things fail. And then one of the mechanisms for subcritical crack, it's not the only one, is called stress corrosion. And often we call that water weakening. And so the idea there is you have these stretch bonds at the tip of a crack. And so there's an enhanced reaction rate that goes on. And so what happens is you've got, let's say we have a quartz there that's getting stretched, and the water will come in and make it a reaction and make this strong bond turn into a weak hydrogen bond. And that's kind of this iterative process with the crack growth. So that's one mechanism that we have for. Anyways, let's show an example. So this is kind of like the flake in the Yosemite one, just to kind of demonstrate. So I take a 1 meter cube block, and I assume a 1 centimeter rock bridge holding it up. So that's a 1% rock bridge again. And I have a stress intensity factor for this. And I have the Charles law. So it's actually quite simple. You just take the K1, you plug it in here, and then you integrate this. You can integrate this one actually analytically if you want, or you can do it numerically in a spreadsheet if you want. You can do it either way. So I take some properties. These are just some properties I used. And then again, what you see is nothing happens very much. So we're going out here to about 1600 years. So not much happening. And then it just starts to accelerate and it fails. And in this particular case, it fails at about 1600 years. And what's kind of unfortunate about this, it's very sensitive to some of these parameters. So if I change that initial crack thing just a little bit, it may switch from 1500 years to, a million years, or go the other direction. And so what I tend to do with this kind of stuff in order, to make it more of an engineering thing is that you can do a probability of failure. And I do a variation in that initial crack length over some normal distribution. And then you can do something like you can figure out what's the probability of failure at 100 years, and it comes out to be like 17%. And then you can change the number in here. You can say what's in 1,000 years, and it might say 30% or something. And so that gives you a little more idea of how to use it in principle. But the interesting thing here is that we can also calculate the velocity. So we have in fracture mechanics, we also have the formula for this particular case for the displacement. So I can get displacement versus time. I can take the derivative and get velocity. This shows the velocity versus time. And then if I take 1 over the velocity, you can see that fracture mechanics is predicting this linear behavior that points to the time of failure. And again, you only need theoretically 2 points. And here I give you a real example that shows you how powerful this thing is. This was an underground excavation, and this was where they had put an extensometer at 3 different anchors, and there was a bedding plane in here, and so it was a weakness plane, and so it was forming like a beam and hanging on that, and so if you plotted the velocity, what you found is these 2 anchors started to go way up. And that's because this first anchor was actually in the block that was failing, so it didn't do anything. It just sat there. And then when I do 1 over inverse velocity, or if I do the inverse velocity, then we find it kind of muddles around. But at some point here, it's a straight line all the way. In this point, 7 months before it failed. 7 months before it failed, it started to show this linear behavior. So this is quite powerful, really. So anyways, I end the talk with just a few. Creative ideas. And, I'm really interested in this idea. I mean, the problem with doing inverse velocity to predict, it's really good if you have the equipment to measure that movement very carefully. The question is, can we do it on what I call an everyday slope? So I have an everyday slope. You have highways, you got thousands of miles, And it'd be very interesting to try to be able to kind of make a prediction. And, we can do it. Do I mention that on the next slide? No, I don't mention it. The stuff I talked about last night with point clouds, you can do point clouds and you can do, you can do sequential point clouds at different times, but it's kind of a pain because you have to get the 2 point clouds all matched up and all this. What I'm thinking of is more non-traditional ways, because when something is moving, other things are happening besides just the movement. You're seeing changes in aperture between the blocks. You're seeing maybe rockfall that's occurring because you got that movement. And you might even see GSI changes, And so you really could plot any of these. You could plot one over the velocity, or one over the aperture rate, or one over the GSI change rate, or one over the rockfall rate. And you might be able to make these kind of predictions. And again, you don't need a lot of data. I showed the example of if we had sort of a consistent rainfall each year, and even if you just took measurements once a year and you tried to do this, what I imagine you'd find is certain places you get like low numbers, like a year, maybe months, and other places you'd get million years because the slope, we know that some slopes just aren't moving, but it would kind of give you kind of a nice way to maybe, anyways, I do that, to do that. And then I wanted to show you this other way. Yeah, if we were interested in something like aperture or rockfall rate, are there other ways to do it besides putting all this geotechnical instrumentation on the slope? Because again, if you have thousands of miles of highway, you're not going to do it everywhere. And I give you this example of the power of the large language model. Students are all using large language models, whether it's ChatGPT or Gemini or whatever. And it turns out there's a thing called vision language models. Like most of the large language models, and first of all, large language models typically have hundreds of billions of neurons, or whatever you want to call those things, weights in there. But they do make some that are smaller that would provide a sensor that could go out in the field. And there's these things called vision language models, where instead of text prompts, text response, or text prompt and a picture response, you put a picture with a prompt and you get something. I just wanted to show this example just to kind of show kind of these things are kind of interesting. This is this one called Phi 3.5 vision. It's a vision model. It's only got 4.2 billion neurons as opposed to these things like ChatGPT. Anyways, I gave it this picture. I just gave it the picture in a very short prompt. I just said, what's going on in this picture? And this is what it gave it back. It said, this image depicts Mountain Road with a section that has fallen rocks on the roadway. That's nice. And then down here, the size of the rocks on the road range from small pellets to large boulders, some large rocks being several feet in diameter. And that kind of got me thinking that, that's what a human being would do. If I asked you, how big were those rocks? You'd say, okay, the highway is about so. You'd have a short thought process that would go on, even in your subconscious, and you'd say, oh yeah, probably a couple of feet or something like that. And so that's what it gave me. And so that makes me think that as these models get better at reasoning, that they can be used as sensors. They can be used as a sensing device where you're not collecting data in the traditional sense. You're just asking you what's going on. And then what's the advantage of that is you can imagine a sensor, and let's say, a deer came down the slope. The sensor probably wouldn't know what that was, but the vision model will go, that's a deer, or that's a bobcat. I mean, it knows what all those things are because it's so much intelligence is gone into those things. I tried to do aperture. I thought, well, can it tell me, can it say that there's a bigger aperture today than there was a month ago? And I gave it this 2 examples. I explained what aperture was with some prompts, and then I asked it to tell me which of these has a larger aperture, or what is the aperture, or whatever. And I told it the size of these blocks. It didn't do that great a job on this one. All it could really get out of it was that the right group of boxes has a larger aperture, and this one is kind of interesting too, because if you look closely, it says that the road curves to the left, which is kind of interesting, So, again, there's a lot of improvement that's going to happen in these, but I just think, and again, thinking of a monitoring device, it's a little different than what we traditionally think about it. In terms of, so then I'm just kind of summarizing in terms of resources. There is a book, Richard Schultz, wrote a book, called Geologic Fracture Mechanics. So it talks about a lot of the stuff I mentioned. In terms of the AI stuff, this is a really great resource. This is a 1,500 page PDF with GitHub, with hundreds and hundreds of GitHub programs in there that you can run. And it's by the guy that's a professor at Harvard that's done a lot of work with all these kind of things, edge AI and language models and all that stuff. Also many papers. This is a field where, again, you can, there's a lot of literature on the stuff I was talking about. So yeah, that's kind of it. I don't have much more to say except that it's kind of a fun topic to get into, talking about these unstable rocks. And I think there's a lot of, clever ideas that may be possible. So with that, I want to thank the AG Foundation. I want to thank the GSA Foundation. I want to thank all the people that put on these, invite the JAWS lectures to come to their places. And I want to thank all the people that come that are here in the audience. So thank you very much, everybody.